Okay, so welcome everybody to the February edition of the CMR Journal Club, and thanks for joining. It's shortly after the SCMR, a very interesting meeting, and I don't know how it felt for you, but it certainly to me, artificial intelligence and deep learning was a big topic, and therefore I think it's great that our focus today is also on machine learning. And before I ask Behzad to share his screen and walk us through his paper, I wanted to say thank you for both of the first authors or corresponding authors to report on their studies. We will start with Behzad. He's the senior author of a study published in the Journal of Cardiovascular Magnetic Resonance. And it's about improved robustness of deep learning-based segmentation of multicenter myocardial perfusion CMR datasets using data adaptive uncertainty-guided space-time analysis. Now, look, this already sounds to me pretty spacey. So it will be not easy. I asked both authors to not to go too deep into the weeds of the methodology, but just so that we understand what it is about. Always consider this just 10 minutes. Walking through what was the key point, what were the key points, and what can we learn from that? Because all the detail, people can go to the paper itself and maybe ask ChatGPT for if they have problems understanding. So Behzad, if you could share your screen and walk us through the first paper, and Marc Vornehm is also already on, will be on in a few minutes.
Thank you, Matthias. Yes, I think I can do that. This is our a collaboration with multiple centers that...
Sorry, are you sharing your screen? At least
yes.
I cannot see it. Is it just me?
It's showing my screen here.
I see it, Matthias.
Okay, great. Yeah.
There may be a tab on the top, Matthias, maybe.
Yeah.
All right. So this is been a collaboration for nearly 4 years with multiple centers to look at the potential for data adaptive machine learning, deep learning to improve the robustness of convolutional neural networks for automatic analysis of stress perfusion, CMR. And as you can see, there's multiple centers that contributed data. We're following up on this work now with the SCMR registry in place, with improvements even on this current work. So the main motivation, if I could zoom in to this paragraph, is that it's known, and this was apparent during COVID, especially with a lot of high-impact journals papers getting published on automatic deep learning-based analysis of chest X-rays for diagnosis of COVID, where people would take the developed algorithms and they would go walk across the street to the adjacent hospital, and the methodology wouldn't work. So this is the concept, and there's a New England Journal paper we're citing here, very nicely described what is the concept of dataset shifts in medical imaging, and how, especially in the context of medical imaging, the developed methods that can be actually practically deployed need to be robust to dataset shifts. So the idea is, specifically, if you have changing characteristics of these external datasets that your network, your trained model hasn't seen before, and that could be related to demographics, a patient cohort, but it could also be in case of cardiac MR. As we know, we love the flexibility and beauty of cardiac MR being such a unique modality with all the different pulse sequences, variations in hardware, field strength. Basically, if you categorize it, it's software differences and hardware differences. All of those could lead to these dataset shifts. So what we're trying to do here is have basically a methodology that can adapt on the fly to be robust to these kinds of dataset shifts. And that's what we believe in, from our side is the right way to think about things when it comes to generalizable, deployable CMR analysis tools, especially in the context of multi-center studies. So just to briefly go through the overall methodology, I hope I can get everybody's attention so we can go through this. So actually, I could start from just saying the top row here is the training stage, which is the technical, description of typically what's done with when you have, say, thousands of examples of a myocardial perfusion, ground truth segmented cardiology fellows and overseen, by experts to correct for these, endoepicardial contours, and thousands of, image series, multiple years and multiple different types of scanners. You still are stuck with this internal data set. And you can split it into a training validation set. There's like a training, basically approach with what, the architecture that's been shown to be the winner in terms of medical image segmentation specifically is this UNet architecture. The key innovation here is we don't train a single model. We actually train a model pool. So in this case, we stopped at 50 models, and that completes the training stage. What's different between these 50 models actually was inspired by Google Brain paper on self-driving cars, where they realized that, this is many years ago, they realized that if they just change the initialization of these stochastic gradient descent algorithms, where, you basically it converge to a set of parameters for these different filters in a convolutional neural network. If you just change the initialization, it will still converge and it will, basically do well on the validation set, but it does behave slightly differently when you change the initialization parameter. So what we could do is we can seed the initialization of the training process 50 times differently, and we get 50 different models. In the next stage, when we are, say, dealing with analyzing data set from, say, Houston, Texas, from Houston Methodist Hospital, where we've never seen, we don't have that exact scanner, we've not had the variation in the pulse sequence they've had, different matrix size, all of that, different patient cohort. That's the external data set that comes in. We let every one of these models to segment or analyze the image series. And each one of these is used, so the analysis technique, as I'll describe next, uses a patch-based approach where inherently it automatically derives a uncertainty metric as part of that segmentation process. And you can boil it down, it actually derives a map, a spatial map of the uncertainty in the segmentation. And we can boil it down to a scalar number on say a per pixel average uncertainty, which is this U sub pp quantity, if we can zoom in. And what we do is in the final stage is we pick the solution of the model that had the lowest per pixel uncertainty. And that's going to be basically the best solution that the approach comes up with. So it's quite different in that the next patient that's scanned on the scanner and is pushed into our analysis technique, it may be that model number 2 is the lowest uncertainty solution. So there's that context of data adaptive on-the-fly selection of the models, which is a deviation from the conventional approach. So here we described like all the different types of data augmentation we do to be as robust as possible to variations and data set shifts just using our internal data set. That's a classic way to improve the robustness of the deep learning-based image segmentation. We do introduce some kind of interesting, types of data augmentation here. And the next is describing the patch-based approach, which is critical to do to actually derive this innovative uncertainty map, as I described. So basically, in a first pass perfusion image series, you can stack the time frames into back to back, and you end up with basically a 3D object, a 2D plus time object. And you can, instead of analyzing the full field of view or the region of interest, you can have, say, 64 by 64 pixel or smaller patches that you can move around in space. And these are individually fed to the deep neural network and segmented, and then you can put them all together, aggregate them, and basically come up, present the final segmentation. This is, again, a classic image processing trick. What's beautiful about it is once you do this, if you look at the overlapping patches that you can shift around in space in, say, this image series here, there is a common set of pixels if you kind of move these things around. And let's say, look at this, say this is the anteroseptal tissue in this stress basal slice, for example. There are many pixels here, if you could see my cursor, that are segmented multiple times by multiple overlapping patches. And now here I've stacked the solutions, the different segmentations that you get by feeding these patches to the neural network. And those little variations you get across the model index will give you an uncertainty map. Basically, if you look at the single pixel and every one of the models decided that this is a myocardial pixel, then you have very little uncertainty. But if out of, say, these 5 or 6 models, one of them decided that this is a blood pool pixel, an LV blood pool pixel, then that pixel has high uncertainty. That's actually reflected in this uncertainty map. You can do a we have a mathematical definition of this. You know, you can read the details later of how this uncertainty map is calculated. And our results are the data set we have trying to get this. So we basically have going back to the table, we have 2 external data sets. One of them had a different vendor. The other one had is an external center with a similar vendor. And we show very different patient characteristics compared to our internal net data set. So stopping here, we're showing the segmentation performance on the left side, panel A and C. Basically, what it's showing is that on the internal data set, our proposed approach doesn't, significantly improve the performance, and that's expected. But on the external data sets, it's a significant improvement when you do this model pool training and model selection using an uncertainty metric compared to the conventional single model training approach. And we do this with the DICE metric, and here we can do it with host of different metrics of segmentation performance. I just want to highlight some interesting examples here. So, for example, here you see it's a representative case of the first external data set where you have basal meat slices, different time frames, and there is a left circumflex endocardial, subendocardial perfusion defect. You can see the manual expert contours are shown here. The single model established approach is here, and our proposed approach here. So we see both methods do well, but if you zoom in, there is improvement in segmentation accuracy in the proposed method. More importantly, when you go to the more challenging cases, this is a hypertrophic cardiomyopathy patient. You see, especially in the systolic slices, it's even hard for an expert, for Matthias to segment these things because it's so hard. There's a very little blood pool, and it's hard really to detect where is the subendocardial contour. So the conventional method completely fails. And what's nice is that it's also reflected in the uncertainty metric, even with the conventional method, because that's a general approach. In our automatic segmentation, the performance is much better thanks to the model selection technique. And this is another case where, from the second external data set, this is a different vendor case from New York Presbyterian, and you see that there is discontiguous contours in the conventional, deep learning approach, whereas our method has, a very high, a much improved DICE score and contiguous contours. Again, all of this is picked up by the uncertainty map and used in the selection process. I can go on, but I just want to highlight that we have 7 or 8 appendices in this paper. Some of them are really important to take a look at, including how this model pool actually has a very diverse behavior when it comes to external examples. And this is the hypertrophic cardiomyopathy case. You can see that across the 50 models, there are very different, the performance is very different, which is quite surprising to a lot of machine learning, deep learning researchers, how just changing the seeding of the initial seeding of the training process can give you such a different performance. And we actually leverage that diversity of performance across the model pool to do our model selection and derive our uncertainty metric. Thank you. I'll stop here and be happy to answer any questions.
Thank you very much. Fantastic. So whoever wants to ask a question, either just unmute or maybe better even raise your hand or type the question into the chat. So there is one from Rebecca Thornhill. Congrats to a beautiful paper. Do you have a sense of what the impact on segmentation performance was on the final stress rest perfusion values?
Yes, we actually, that's an excellent question. It's a, this is JCMR, so no paper can get published without actually providing, that's why it's high impact of actual quantitative metrics. So it's in one of the appendices where we show the correlation. So this is the first external data set, which had a dual bolus acquisition. So we actually could do fully quantitative analysis, and we have they showed an improved correlation in myocardial blood flow analysis, stress blood flow, both in terms of R-square Pearson correlation and also the Bland-Altman limits of agreement. Yes, so it does improve things. It would have been more dramatic in the second external data set because of the different vendor and much more challenging cases. Unfortunately, that was an older data set and didn't acquire accurate AIF, so we couldn't do the fully quantitative analysis.
Okay, yeah, thank you very much. We will have to move on sometimes, very soon, but just from my point, so I think it's a very elegant approach. What I also like that not only that you introduce uncertainty as something that we also do as humans, that or should do more, that we point out the reason why we're not exactly so. But the question I have is, have you ever thought about how we could translate this information? So you generate the uncertainty maps, but could we somehow put that into the image itself? For example, like blurring that area. So I don't want to necessarily have an answer, but just wanted to know what you thought about that, because at the end of the day, there is always a certain black box anxiety. So if you somehow translate this into visual information that everybody can understand, that improves adaptation or acceptance in the field.
Exactly. So this first author, Dilek Yalchinkaya, who is actually on the Zoom here, is working on that, and we actually can leverage this uncertainty map and highlight in the final solution, in the final segmentation, the segments that are that the methodology is detecting as uncertain. So it's a form of explainable AI, Matthias, at what you're pointing to, and that's the advantage of having this. So what I would like to point out also is that we have a GitHub page in the paper, and I think it would be great if this can be extended to other CMR applications. We don't have the bandwidth to do it all, but it would be great if it's followed up. And to your point, wouldn't it be great if, for example, for LGE analysis, you could actually highlight where the more uncertain areas are, where the expert end user can actually correct those and look at it in the final report.
Yeah. Okay, fantastic. So thank you so much. So the next one, the next paper will be presented by Marc Vornehm, now with Siemens, but this paper is together with a group of Florian Knoll, and it's called CineVN, Variational Network Reconstruction for Rapid Functional Cardiac Cine MRI. So here it's not so much about the analysis, but about the reconstruction of the primary data into images that is improved by a deep learning algorithm. Marc.
Yeah, thank you very much. First of all, can you hear me and see my screen?
Yes,
perfect.
Both.
All right. Yeah, thanks for the introduction. And as you said, this paper was in collaboration with a couple of institutions, FAU, Florian Knoll's group, as well as Siemens Healthineers and Ohio State University. And as a disclaimer, as you just said, I am now an employee of Siemens Healthineers, just to start with this. So as you all know, we very routinely do cine imaging in order to get a lot of quantitative metrics, ventricular volumes, myocardial strain, and commonly these require long breath holds, and this can lead to motion artifacts or is even infeasible for a lot of patients, as you all know. So there's always the aim of accelerating cine imaging up to real-time cine imaging, which has seen a lot of improvement, a lot of research over the last decade, you could even say, but usually at the cost of lower spatial or temporal resolution. And to reconstruct these real-time cine images, you usually use compressed sensing or some other methods, but all of those methods, what they have in common is that they exploit temporal redundancies in the data. So that's basically the reason why we can accelerate cine imaging this much, because most of the pixels or most of the information in the data actually doesn't change over time. So we can exploit this temporal redundancy in our data. But this also leads to temporal blurring on the other hand. So this temporal blurring, of course, corrupts the motion that we see in the data. And this also has an impact on those metrics that we love, on the volumes and especially on strain. So it's difficult to quantify strain and volumes on highly accelerated data. And this has been shown by several studies that indicated biases in these metrics when you compute them on highly accelerated cines. So in our reconstruction method, we had this in mind the entire time and focused in the evaluation on evaluating these functional metrics to see how our method performs in this regime. So our method is based on a variational network. So that's a very common unrolled network architecture for MR image reconstruction. And it's based on this optimization problem that you all know if you're working in reconstruction. And the VARNet or VN unrolls this optimization problem in a gradient descent optimization scheme for a fixed number of iterations, which we then call cascades. And then in each cascade, you have a data consistency term and a regularization or refinement term. And the idea of the VARNet is that this refinement term is basically some convolutional neural network. So what these architectures look like is roughly like this. We have multiple cascades. So this is a cascade with a data consistency term and a refinement term. And inside of this refinement term, there is, in this case, a UNet. So we use this method and apply a couple of modifications in order to improve performance on spatiotemporal data, in order to improve data consistency, and in order to improve network training stability, which helps with this high-dimensional 2D plus T data. So the network architecture that we use in each cascade, as I said, is a UNet. So that's more or less standard. And instead of 3D convolutions or something like that, we use 2D plus T spatiotemporal convolutions. So that means we apply a 2D spatial convolution, then an activation function, and then a 1D temporal convolution. So we separate those dimensions. The units themselves are comparably small, so we only apply downsampling and upsampling twice per unit. Then we have basically 3 modifications that I will very briefly go through. And in the supplementary material, we also have an ablation study where we show the effect of each of those modifications. So the first is what we call KT-weighted refinement. So this is basically a learnable weighting function that we apply in KT space and that we multiply on the output of the refinement term. So yeah, the output of the refinement term is in K-space, and then it's just weighted differently in different regions of K-space. And this weighting function is a learnable parameter. So I will briefly switch to the supplementary material because we have some representations of these weighting functions after learning. And I think it's quite interesting to look at those because so these are the weighting functions after each of those 15 cascades. And you see that in some cascades, you see that basically each cascade can now focus on a specific part of K-space. So we have some cascades where the weighting of K-space periphery is higher, and we have some cascades where the weighting of K-space center is higher. And so this allows our network or each cascade to focus on regularizing some part of K-space. The second modification, very short, is phase cycling. So it's basically augmentation or an additional means of regularization by applying phase cycling on the data that goes into the UNet. I won't go into more details here because it's not that interesting. What is more interesting, I think, are conjugate gradient blocks that we inserted into the variational network architecture. So the problem is that our data is highly diverse. So it varies in a lot of parameters in terms of image size, in terms of number of phases. And this makes data consistency in the way that the variational network does it difficult. So we needed to improve data consistency, and we do this by inserting these conjugate gradient blocks after each third cascade of the VARNet. And in these conjugate gradient blocks, we basically solve a separate optimization problem. And in this separate optimization problem, we search for a solution that is, on the one side, close to the acquired undersampled k-space data, and on the other side, close to the output of the previous VARNet cascade, so close to the current estimate of our reconstruction. And this helps us to avoid local minima of the optimization problem, and it improves data consistency when our data is highly diverse. So we trained this network on publicly available data from the OCMR dataset. That's fully sampled cine data from Ohio State University, highly diverse between 0.55 Tesla and 3 Tesla, and different resolutions in terms of spatial resolution, different temporal resolution. So that's a quite nice data set. And we train networks for different acceleration rates between 8 and 20. I will quickly go to the results of this retrospective study. So we computed was PSNR and SSIM on our reconstructions as well as on reconstructions from a plain variational network and some compressed sensing reconstructions. And to make it short, basically our method gives the best results across metrics and across acceleration rates. So now more interesting, of course, is prospective data. So we had 2 different prospective data sets. One is on healthy volunteers and one is on patients. And in the healthy volunteers, we acquired reference data using Grappa, and additionally accelerated data over 2 heartbeats and accelerated data over 1 heartbeat. And then we can compute functional metrics on all of these data and compare. And what we see is, first of all, that the images look nice. And if we look at the functional metrics, so in these plots on the left, what you can see is the 3 protocols. So the Grappa reference, and then the 2-shot protocol and the real-time or single-shot protocol. And yellow is our deep learning reconstruction. Blue is a vendor compressed sensing reconstruction, and red is a temporal total variation compressed sensing reconstruction. And what you see is that in compressed sensing, metrics like the ejection fraction and also other metrics are underestimated. And our deep learning reconstruction gives metrics that are closest to the reference Grappa reconstruction. And this is the case for ejection fraction as well as for other volumetric metrics, and very interestingly for strain. So we evaluate peak radial strain and peak circumferential strain. So yeah, to cut it short here, we also see this in patient data. However, we don't have a reference in this patient data, but it's interesting to see it there as well. Yeah, so our network allows a high temporal resolution and high spatial resolution with only 1 or 2 heartbeats for the acquisition, and still enables good estimation of those functional metrics. And I just want to point you also to a GitHub repo. So we published all the code and a couple of trained networks, so you can try it out yourself.
Thank you so much. While some of that was definitely way above my level of understanding, but it's fantastic to see that you were able to so efficiently deal with sparse data and still come up with accuracy that on a clinical level would be absolutely sufficient. And especially if I think about real time, it's not only the time saving, but also would abolish the need for averaging at all, and the image quality probably would then be good enough. And if we use then also deep learning informed analysis tools, then we get the best of both worlds. Are there any questions from the audience? I would, of course, be curious is whether this finds its way into commercially available tools now.
Yeah, so we are planning to evaluate this further, of course, yeah.
Mm-hmm. So that it will eventually, that techniques like this can also then be used by people, everybody out there. And where do you see the next steps? Let's say this works also when applied to various patient groups and stands a clinical validation. Do you think this requires further refinement of some details here of the model, or change of parameters which you could afford to change? Or do you think this is now for a while something to apply in a broader setting?
Yeah, so that is definitely something that we need to evaluate, and I basically skipped over the patient study, but we definitely will need more elaborate studies in patients in order to evaluate those things that you mentioned. And I would be interested in also seeing. Well, I would like to evaluate further which of the changes of the architecture are actually most relevant for this high temporal fidelity that we have in the end. So all of them improve the reconstructions in like on the retrospectively undersampled data, but I'm not sure which of those modifications gives the most benefit in terms of functional metrics in the end.
Yeah. Okay. Thank you very much.
Hi,
both.
I have a couple of
Yeah,
questions,
yeah.
if the time
Sinan,
permits.
Go ahead.
Thank you for the nice talk. So one of my first question is, so the output of the network, is that a complex image? Like, do you process this as two-channel image? Because in the original end-to-end VARNet network, they do a sum of squares reconstruction on the predicted case space to get the real valued image, right? But in your case, do you work with the real valued image, or the output is the complex image?
Yeah, so we work entirely with complex data. So there's always two channels to represent the complex data. And also the output is complex data. And then we, like in the very end, we take the magnitude of those images.
Right. So the loss function that you compute, is that over the real valued image?
One more question, and then we have to probably wrap up.
The loss function is also computed on the complex images, yes.
Oh, I see.
So, yeah, this is on the loss.
Okay, thank you very much. Unless there are any other urgent questions, I would also suggest that we can leave the chat on here a little bit, if in case there is an urgent question, could put that in, and maybe Marc and Behzad could stay on for that. Thank you both, Behzad and Marc, for the challenging, at least for me intellectually, very challenging, but very interesting and so relevant presentations of your research. And we will have a March edition. Nicole Seiberlich will host that. I don't have yet information what she will present. I will be back then in April, where we will talk about featured research on CMR and hemorrhagic infarction with work from Rohan Dharmakumar's group. But for the March edition, stay tuned on the website. We will post that as soon as possible. Thank you very much, everybody, for joining, and again, especially the presenters. All the best. Bye-bye. Ja, vielen Dank, Marc. War für mich so die Hälfte vielleicht zu verstehen, wenn ich angeben will. Wahrscheinlich weniger, aber trotzdem sehr interessant.
Ja,
Okay,
gerne, gerne.
ja. Also dann bis bald.
Ciao,
Bye,
ich beantworte hier
Willi.
gerade noch eine Frage, ich bleibe noch drin.
Ja, go ahead.
Hi, Mark. I think I sent you one question on the chat.
Yeah,
I
I'm writing the answer right now, but I can also reply here, of
okay.
course. So we
Okay.
used a trophy strain. That's a tool from Siemens.
Or true fist. Oh, I see.
It's
Okay.
called a trophy strain. Yeah.
So is that open source or you have to buy the subscription for that?
It is not open source, but
Oh.
I do not know like what the let's say the preconditions for buying or for obtaining it are. So
I
I
see.
don't know if it like
Okay. Yeah.
I don't know. So if it's probably best to contact your Siemens collaboration manager if you want to use that tool. They can provide you with information for that.
Okay. Sounds good. Yeah. Thank you so much.
Thank you.